Well, good morning, everyone, and thanks very much for coming to this talk, even though it's kind of early in the morning. My name is Neal Ziring, and I'm going to try to give you a talk today on applying security engineering principles to complex composite systems. I know that sounds like a dry and boring government title, and it is, but I'm going to try to liven it up a bit with a few anecdotes. Okay, now I have more time. That's great. Okay, so here's my little obligatory outline. The size of the font is how much time I'm going to spend on each section. Okay, so the purpose of this talk, and it's a keynote, right? So I kind of had to keep it high level, is to talk about security when you need to apply it to big, complex systems. You know, and many of us in our career will write, small, I need it fast, simple systems, and we'll write big, complicated, multi-part systems, right? We all do that. This is really focusing on that far end of the spectrum where you have a very large system with lots of parts that are heterogeneous and run on different platforms, and they all have to work together, and it ultimately has to be secure, okay? Use of simple security techniques, that we learn in school, or when you go to a website and it says, hey, validate your form inputs. Those simple rules are very important and useful, but I contend that they're not sufficient by themselves to make a large, complex composite system secure. Now, in addition to the systems that we build getting more complex, right, they need to operate in more complex environments. If you think back to, say, 10 years ago, the systems were already pretty darn complex then, but at least most of them were running on your own premise. and nowadays, that's almost never the case, not even in government, and certainly not in private sector. And secondly, to establish security for a large complex system is hard enough, but then you have to maintain its security over time. And that's where these security engineering principles can really come in handy, because you can ask yourself as you're doing changes to your system or adding new functionality, did that principle that I chose for my system, does that still apply? Okay. Okay, so who am I? Right, Ben gave you my title. I've been at NSA for 31 years, all but a few months of that in cybersecurity in one form or another. I've worked on the security for many large NSA mission systems and composite system designs, and later in my career on various boards that look at the design of such systems and approve them and things like that. I've had the privilege at speaking at OWASP events twice in the past, once here in DC and once out in Denver. And when I got this invite, I was very excited because I have a great deal of respect for OWASP and the work that they do for the community. I'm involved in a number of software assurance, software security activities within the Department of Defense. And when we're thinking about like source material, OWASP is always a reliable place to get that. And my hat is, if I was wearing a hat, my hat would be off to OWASP for what they do for the security community. Okay, something I'll add to my background that try to make things a little bit fun here. I've been working on web security sort of on and off with other security since the first release of the Mosaic browser. Now, those of you who really know web history remember the Mosaic browser, written with the Motif toolkit on X Windows in, mid-90s or something. It was, very basic and rudimentary by today's standards, although it had a bunch of features that Chrome still doesn't have, but whatever. Even back then, we were looking at this new thing called the web and saying, is this going to take off, or is everybody going to stick with Gopher and FTP? And we realized right away that security was going to be an issue. And me and my colleagues being at NSA, the first thing we thought of was, well, why isn't this encrypted? So the first web security project I ever worked on was an attempt to encrypt HTTP sessions, and we, hacked up a server and we hacked up the browser, and of course it was NSA, so we had to use hardware for the encryption and all that kind of stuff. It was a lot of fun. And that was well before SSL was invented. And we later, showed people what we had done, and like, thank God we didn't do it that way, because we tried to put layer the encryption on top of HTTP, which was like a huge mistake. Putting it underneath, as SSL and TLS do, is definitely the way to go. And I'll try to tell some more anecdotes as we go along. Okay, composite systems. Why are today's systems hard to secure? There's a whole bunch of reasons, right? And if you work in these systems, which most people at an event like this would, you know why this is, right? The number of diversity of software components is just sort of through the roof. Long gone are the days when you write like your entire big complicated system in one language on one platform using one toolkit. I talk to students when I go recruiting, and their class projects are like that. But projects out in the real world, certainly the ones I'm familiar with within government, are not like that anymore. The diversity of internal interfaces. Your external interface might be very homogeneous. It might be I'm going to present a web service, and I'm going to keep it clean, facing outward. But your internal interfaces tend to be very complicated, right? And they're of diverse types. Right? You might have some that are like RESTful services. You might have some that are message brokers. You might have some that are basically a bunch of components talking to an SQL or column store database. You might have, some kooky built in-house file passing service. We have one at NSA, and we open sourced it, so all of you can enjoy it too. It's called Niagara Files. Get it from Apache. Some friends of mine worked on it. So, you have all these diverse internal interfaces, which raises the complexity of your code because you have to deal with them, okay? There's the diversity of components and frameworks and platforms and management tools. My dog woke me up early this morning and I couldn't get back to sleep. So I was just like browsing, technical articles and crap, and I read one about a cascading failure in a Kubernetes system where all the different agents that these particular folks had layered on their system sucked up all the resources and caused this cascading failure. And I'm like, wow, why did they need all those agents? But every one of them, they had a reason why it had to be there, right? So there's a variety of types of entities that depend on your system, right, to deliver them trustworthy data or to provide them a service. External providers, right, obvious. And lastly, the variety of security controls that you might impose on your system, or that regulators or compliance regimes might require to be imposed on your system. In NSA, right, we're an intelligence agency. We have tremendously complex compliance regimes that we have to comply with, and all our systems have to implement those. Okay, well, not all of them, but most of them. The ones that serve up the cafeteria menus and stuff are a little less. But so that variation can drive complexity as well. And think a moment about sort of modern development environments. The other day I was just trying some hobbyist stuff at home. I was trying to learn to use serverless compute on a cloud framework. And I said, hey, I'll just fire up Eclipse and try to write some code, follow a tutorial. And just downloading the dependencies took multiple minutes. And I wasn't even on Wi-Fi. I had actually plugged in the Ethernet cable. So, I had no idea what was going into this thing. It was kind of like, whatever Maven Central thinks is good, that's what's going in there. That's fine for a hobbyist project. Telling a government auditor, yeah, I just put whatever software in Maven Central thought was appropriate, maybe not a sufficient answer. Okay, so the proliferation that we see in sort of modern software development environments, while it's great for productivity, can complicate the security picture. And we'll talk more about that just a little bit later. Trust relationships is another aspect. when I look at how modern adversaries are attacking modern systems, they're often exploiting trust relationships. And we'll hit that in the principles as well. Yeah. And of course, this is my favorite part. Each of your trusted parties that you trust, they trust other folks, right? So you have this kind of whole transitive thing going on that, can expose your system to a risk that you didn't think you had, right? And we've seen that in a number of high-profile breaches. Okay. Another aspect, I probably went on too long with this whole complexity thing, I apologize, is the types of sort of entities that use your system, right? If we think back to the old days, you had one kind of user. It was a human being coming to your system with a browser, and you serve them content. Nowadays, you still have those, right? Human users, they're coming from a variety of browsers. But you also have mobile apps that are trying to hit your system. You have non-people devices that you may have to deal with, like Internet of Things devices that are calling your services. And they have different needs than the human beings. And then you have other web systems within your company or within your government agency or with your partners that are attempting to call your system to get some service. Okay? I talked about policy and regulatory complexity, right? That took kind of a big jump with the European GDPR being introduced a year or two ago. There are higher expectations of scale and resiliency today, right? Everybody expects your system to be up all the time. Now, many enterprises choose to go to a cloud provider to get that scale, and that's fine, but that introduces its own complexities because now you have to configure your security sort of not necessarily with your on-prem tools, but whatever policy and control tools the cloud provider happens to offer. And those may not be the same from provider to provider. Okay, and then lastly, there's your whole build chain. Whatever form of continuous development or continuous integration you might be doing, those systems nowadays tend to be very closely connected to your production systems, and do they represent a path whereby an attacker can get in to your system? Okay, so in the principles that are coming up, we're going to use this example, and I'm going to refer back to it. I wanted to put the actual U.S. signals intelligence system in here, but it wouldn't fit. But it is a large, complex composite system. I did a lot of security architecture work for it about a decade ago. And so this is a smart city example. It's adapted from a number of examples that I found in the academic literature about smart cities. And I've been studying Internet of Things in sort of my day job for a while. So I thought this was a fun example. So what's going on in this puppy? You got the kind of the users at the bottom, passengers who want to buy tickets and ride on the subway, and that guy is running because he's about to miss his train. And of course, there's a database that holds the user information. Then you kind of have the management system in the center, and it has its own database, which probably isn't the same type of database as the one below it. You have some city officials who want to administer and oversee this whole business. You have the whole ticketing system, right, which has to deal with money and credit cards and all the regulatory complexity that comes with that, as well as with these devices that are sort of placed all around the city and probably connected to the internet in 19 different ways. You got an external weather provider. You have the buses and subway trains and traffic lights and parking meters and all those devices that are feeding you telemetry. And then you have the transit engineers who want all this data and have their own systems that they need it supplied to. So, and I wanted to make this even more complex, but it sort of exceeded my PowerPoint skills. But I think, but let's just, this is not sort of that complex by modern standards. How many people would say that this level of complexity is sort of comparable to the kinds of systems that you build or test in your day job? Okay, a few. And a few of you were probably saying, no, the stuff I deal with at work is way more complex than this, which is certainly true of my stuff. But like I said, PowerPoint is limited how much you can fit on the slide. This one's reasonable because it has a lot of potential vulnerabilities, right? You can see it just by looking at it. You got a whole bunch of internal interfaces with arrows going every which way, which is, in my experience, very realistic. You have databases, multiple of them. You have different types of users with different rights and different privileges and different expectations. And you have different interfaces, right? You have a regular web interface for browsers. You got, mobile apps. You have interfaces out to separate devices like buses and trains and ticket machines. So I think is reasonably realistic. So everybody's memorized that. We're going to go on. Okay. So another important thing, one of the first principles we'll hit, is that security is about mission, right? We build security into our systems because that system has a job to do. So the first thing you have to know about a system where you're going to secure it is, well, what job is it expected to do and which things are more important than other things, right? So for this system, job one is safety, right? We're talking about buses and trains running around a city. Safety is paramount. Next, we got a privacy thing, right? This is holding information about people, so it's got PII. So we have privacy things that are imposed on us by policy or state law, et cetera. And then you want to optimize the services and the revenue, right? The city needs to take in money to maintain the system. And then, sustain the trust of the citizens. And important, but less important than the other things, get the passengers where they need to go as fast as they can. Okay, so let's move on. This is just a restatement of some of the inputs and outputs. I like to draw this sort of diagram for systems that I work on so I can kind of enumerate what are the pieces of data they're expected to be feeding this system, what are the types of users that it's expected to serve, and what external systems depend upon it. Understanding those dependencies has bitten me and colleagues of mine in the butt any number of times. I'll give an example or two as we go forward, but it's exceptionally important to understand what those external systems are counting on your system to provide to them, right? And how that imposes security requirements on your system that maybe didn't apply to the human users. Okay, so this is the best part, the actual principles. Now, the principles here are all sort of standard security engineering principles, but I read an article a couple of months ago, and I really liked how the principles were stated in that article. So in most cases, I've adopted the form of wording that Dr. Sajri used. And by coincidence, Dr. Sajri was actually a colleague of mine at NSA back in the early 90s. He worked there back then, and on security engineering, in fact. And then he went off to like the research community and other stuff. But he's still doing security engineering today, and he decided to capture his knowledge in a book. So I'm in the middle of reading the book, but that's the article. So why use principles, right? And this is kind of a serious question. A lot of folks that I have seen in my experiences within government do security engineering by what I might call a checklist approach. They may have a approval or accreditation set of boxes that they have to check, and they approach the security of their system by saying, well, I've got a box here that says I have to have user authentication, so I'm going to put that in. And then I get to check that box. And that's not a sound way to go about making your system trustworthy and accomplishing the mission that that system is intended to do. All it really achieves is checking boxes. And what I've found, especially when I came in to be the security architect on a troubled project in 2006, was that approach doesn't work. It doesn't lead to systems that actually are secure enough to hold the sensitive mission data that you need them to hold. So we create a very wide variety of systems, and simple rules are cool, right? You know, validate your form inputs, remember to log key events, all good, but it's not sufficient. If you're going to be engineering complex systems, you need rules that are general and applicable to those complex systems, right? So sanitized form inputs is a simple rule of thumb that derives from a more general principle of don't trust externally supplied data. And as I said earlier, the most important thing about picking the principles that you're going to apply for your system and then applying them consistently is not at the beginning when you're building the system and you understand all the parts, but like a couple of years later when you're trying to maintain it and it's grown and it's gotten more complex and it's interfaced to more other things. And that's when sticking to the principles really matters, okay? So, principle number one, we apply cybersecurity in order to make mission go, okay? You know, within NSA, we have tons of different systems, right? I'll just pick one as an example. Particular one I'm thinking about holds data from red teams. Red teams go out. I mean, you've all probably dealt with red teams. They go out, they collect data about a system, they bring it back after they've done their attacking, and they need to be able to write reports and understand the vulnerabilities they found and all those other things. But that data is very sensitive, right? That's data about the vulnerabilities of a real system. And it needs to be protected, it needs to be tracked, who used it and how. So, you know, the mission goal in that case is prevent that vulnerability information from falling into the wrong hands. Therefore, you know, that system has to have certain security controls. Okay? So understand the mission that your system is intended to provide. And it's sometimes easy to get away from that when you're sort of down in the bowels of coding some particular component. But, you know, try to lift your head every now and then and say, okay, what's the big picture here? I'm building this, you know, particular web service that's going to serve a mobile app. But, you know, what's the bigger purpose being served by this whole, you know, agglomeration of containers and web services and databases? In the example, right, the mission purpose is getting people around the city safely and protecting and preserving the city's investment in transit. And so, you know, all of our security principles should somehow trace back to those mission purposes. Okay? You craft your security to protect the mission functions, prioritized by mission importance, and you might not add some features because they would conflict with your mission purposes. I've got a jokey example. I think it's on the next slide. Yeah. Okay. So, I'm sorry, that first bullet's kind of obvious. You know, it's not just about installing everything you possibly can, and we'll talk more about that later. In the jokey example, residents of our city would love to be able to adjust the traffic lights so that they get green all the way to work, right? But that might have some safety implications for all the other people on the roads. If, you know, individual passengers get just like be blopping the traffic lights anytime they felt like it. So we're probably not going to include that feature because it optimizes for goal number 5, improved transit times, at the cost of goal number 1, you know, which was safety. All right. So, security about mission. Now, if you really understand, and this is actually a failing that I remember from earlier in my own career, we were developing communication systems for military folks, and you know, NSA culture, we were all about confidentiality, and man, this data is going to be encrypted, and it's going to be encrypted really well, and we had a good understanding of how other nations tried to break our encryption. We weren't going to let that happen, and we forgot that the thing that mattered most to these military users was that their radio was up and available when they needed it. okay? And that was a case where we sort of let security controls that we knew a lot about how to make and build run away with us, and we weren't thinking about the end mission that that system was supposed to be providing. Okay, we're better about that nowadays. This was a long time ago. Okay, principle number 2. Security is about understanding the risks to your system and then mitigating them. And this is a step that I've seen people skip, and it certainly applies in the sort of checklist approach, right? If you're just checking boxes, you don't know what risks your system is really facing. You're checking boxes. So let's see if I can think of another good example. There was a system I was working on. I ended up being the security architect of it later, that was intended to accept a whole bunch of sort of real-time data from basically a combat zone, dangerous area, and be able to provide sort of real-time warning or real-time alerting to military members if some event was happening that was of interest to them. And that particular system accepted data from a whole bunch of different parties who were going to rely on our system to protect that data, right? This was data they never shared before. It was purely local, but now they were going to consider sharing it into this sort of large pool so that we could give better alerts and more complete, more informative alerts out to soldiers and stuff. And the person who was running that development program found that if he couldn't clearly elucidate to these other information holders how his system was going to protect their information, they weren't willing to share it. And so we had to understand what risks they thought were important to their data, and then be able to build the right security controls, in this system, so that it would mitigate the risks that they were worried about, and so that we could clearly explain to them, yeah, if you share your data to us, we're going to protect it in the following ways, right? It's classified, so we're going to do that, and only people with certain type of mission are supposed to see it, so we're going to do that, and we can only have it for 2 weeks, so we're going to do that. So that was critical, and then once we could clearly explain that to these other information owners, they were willing to put their information in our system, and it saved a lot of lives. So we had to understand not only the threats that we envisioned, but the threats that these other people who owned the information envisioned. Okay. And the other thing is, it's really important to understand the impact of a threat. Right? You may say, okay, I'm worried that an attacker might come at me and deny service to this component. What would the impact of that be? And if the impact is low, you might not choose to invest a great deal in protecting that component, right? Because security ends up being about trade-offs. You can't always provide all the security features that you might want, because you got a job to do. You got to get this system out to customers. Yeah. Okay. This bit's important. So, when you think about this particular principle, it's sometimes helpful to think about a risk that might apply to data in your system, and that long-winded example I just talked about was about risk to data, or risk to the compromise of the control of your system. Right? So what are impacts to control? Most typical one that we see in web systems all the time are injection attacks, where an attacker could come to your system and inject something. Okay. For what? Sorry. He's like, oh, okay, sorry. I thought you were telling me I had 4 of something. Sorry. So, right, we all know about injection, command injection and SQL injection, lots of bizarre types of XML injection. I used to study XML a lot, so I thought those were really cool. So that's about control, right? If an attacker can inject a scrap of shell code that is going to end up running on your server, they've managed to introduce some code execution that you didn't want and is probably going to do something nasty to your system that is going to be harmful to your mission. And then impacts or compromised data we'll hit in the next slide. And then lastly, impact or compromise of access. And this is one where some users are counting on your system being up for them, right? They need to catch their train to work, and they need to buy a ticket. And if your system isn't there for them, then and these that one obviously is availability. So if you understand how these impacts harm your system or the mission that you're trying to get your system to perform, then you'll better be able to craft security measures that will reduce or eliminate those impacts. Okay. Now we're going to focus on data for just a moment. And this is an exercise that I've used in security engineering and security architecture context several times, and that's find the crown jewel data. Okay, and it doesn't always show up where you'd expect, I think, is the lesson I've learned from doing this a lot. So crown jewel data, and there's lots of ways to think about it, but I just picked a simple one for this presentation. The bottom axis is how important confidentiality is for your data. And it's if confidentiality is compromised, unauthorized parties got hold of this data, how high is the impact? Not much impact on the left, very, very serious, grave impact on the right. And then the vertical axis, same thing for integrity, right? If someone could compromise the integrity, then higher up impact is very serious. So your crown jewel data, well, let's look at bottom left corner is stuff that you don't much care about the confidentiality, harm is low, integrity, harm is low. So cafeteria menus. Somebody changes the ravioli to something else, not a big deal. Something where the integrity is very important, but the confidentiality is not, is time, right? Many of our systems depend on an accurate idea of the time, and but it's not confidential. Everybody knows what time it is, just not allowed to change it. It's supposed to be accurate. So that's kind of up in the top left corner. Your crown jewel data is the stuff in the top right corner, where the confidentiality impact is very high and the integrity impact is very high. And so one exercise that you can go through for understanding your risks is identifying that crown jewel data and then saying, okay, if there's anywhere in my system that's handling the crown jewel data, then I'm going to pay extra attention to testing it, to ensuring that it has proper controls in place, that it has proper logging, et cetera. Okay? So let's think about the example for a minute, the smart city system. What's the crown jewel data there? The credentials for the traffic control system, the thing that lets you adjust the transit schedules and the parking meters and all those, the credentials that let you do that stuff, that's crown jewel data. Anybody gets hold of that, impact's very high. The passenger trip records may be crown jewel data. Maybe not. They certainly have privacy impact or regulatory compliance impact if they're compromised. And the PII about the passengers. The telemetry data from the buses and trains is probably critical to both safe use of those vehicles as well as managing them in a way that is good for keeping them running, like maintenance. So that may be very important, but that one maybe not. Maybe the telemetry from the bus is not that confidential. Anybody can observe the bus going down the street and say, oh, there it is. But the integrity might be very important, okay? If I can reach in as an attacker and alter the telemetry data so it always says the bus has plenty of fuel, after a few hours, that's really going to disrupt the bus system because nobody's going to fuel up the buses and they're all going to stop running. Even more, plenty of examples in the train system as well. Okay, number 3. This is one of my favorites. And my friend Rob is a big fan of this one as well. Understanding security depends on understanding forms of attack. An old mentor of mine, who's actually also a mentor of Sammy and is mentioned in the foreword of his book, used to joke with new hires at NSA, what's a 6-letter word that begins with A that means evaluate? And everybody like, what the heck is that? Right. And then he would shout, attack. Because he felt, and I still agree with him, that the best way to really understand the security of a system is to understand how it can be attacked, or ideally even try to attack it and see how successful you can be. Okay? Now, there are many common types of attacks, especially in areas that have been sort of well studied, like web security and cryptography. Understand those common types of attacks, right? And the malicious tradecraft that sort of depends on them. OWASP, for example, publishes an excellent top 10 web vulnerabilities. If you're thinking about web security, that's like the best place to start, is understanding how each of those vulnerabilities work. And think about, if you were an attacker, how could you take advantage of them to gain advantage for yourself or to harm a system? Okay. Next, think about your particular industry sector, right? So I'm in government side. Look at successful attacks in that sector and think, hey, what did the attacker do there? And how were they successful? And would that same tradecraft work against my system? Okay. And that's kind of cool for that sort of thing, being an NSA, right? Because we have both a cybersecurity mission and an intelligence mission that is about, quite frankly, exploiting foreign intelligence targets in order to gain intelligence. And so I always joke that, hey, if I don't have to wonder what a nation-state attacker might do in a given situation, I can go down the hall and find one and ask them. So that's kind of fun. But in complex composite systems, the attacks are often correspondingly complex. Okay? So, there's always that old adage that the attacker has to, the defender has to cover everything, the attacker only has to be right once. My experience in looking at attacks on complex systems, that's not quite true anymore. The system complexity usually means that the attacker has to be right a couple of times, 2, 3, 4 times, in order to reach maybe that crown jewel data or that critical functionality that they're trying to interfere with. And so that's an advantage to you as a defender. You have sort of multiple chances to block that attacker, right? Maybe prevent injection at your initial user web interface. But what if that succeeds? Well, now they're sitting inside a Docker container where my web server is running. How do I prevent them from making that next step, like back to the database, and so on? Okay. So in the smart city example, if an attacker was intent on corrupting the bus system so that they could demand ransom from the city, which I think we all agree that's a reasonable scenario these days, they might start with the passenger website, because that's public, anybody can access it, jump from there to the trip information system, which depends on information from the bus operation system, and once they're in the bus operation system, they can, screw up the bus schedules and cause the buses to run out of gas and all the rest of that kind of thing. Okay, 4. This is one that we apply religiously at NSA. Assume that attackers already know the structure and operation of your system. If you're in a security meeting with your friends or clients, or enemies, whoever, and they say, well, we don't think that this interface over here is subject to attack because nobody knows it exists. You can throw the BS flag, okay? Don't assume your attackers don't know that how your system works, because they will. And they can gain that all kinds of ways. I've talked to our red teamers, for example. How did you figure out how that military system works so that you could get into it. And they're like, oh, well, we just went around on a bunch of websites and some dude had a year-old presentation where he explained the architecture of the whole system. Okay. Another reason why I didn't get to put the architecture of the U.S. SIGINT system into the slide deck. So, you got documentation that's unwisely posted. How many times we read about people leaving stuff in like public cloud storage buckets that attackers could go and pick up. A classic one in web systems are error messages. You make your web error messages really detailed, and they expose, what software you're using and maybe what version and how your code is structured, because they give a whole back trace of where the failure happened. Logs. I've heard of attacks where attackers were able to find where the logs were backed up, not the primary location, but the backups, and go read the logs and understand the system from that. And then, of course, some systems can just have information leak vulnerabilities. And you may not think an information leak is a serious vulnerability, but that's what Heartbleed was. It was an information leak vulnerability. So that in that particular case, exposed crown jewel data like passwords. So don't rely on security through obscurity. Yeah, so start with that premise that the attackers know all your internal interfaces. They may not be able to reach them, but they know they're there. Okay? I went to a really cool talk about attacking a cloud system a couple of years ago at the RSA conference. And there was a lot of that in there, where that particular attack, they just went after like internal interfaces that were insufficiently protected by, in that particular case, cloud policy. And you had to know it was there in order to attack it. But you kind of have to assume that they know that stuff. Okay, names of assets, names of APIs and what parameters they take, all that stuff. Don't consider that stuff secret. And there are some things you do have to consider secret. We'll talk about that in a minute. But this stuff, don't think of it that way. Okay. Oh yeah, there it is. There are some things that you got to think about as secret, but you should keep those things small and then protect the heck out of them, like the private keys that support, your SSL or TLS interface, passwords, tokens that you may get from another system that permit you to access that system for some period of time. Those things you should be more careful with. I mean, we've all heard horror stories about people leaving secrets like this in their code repositories, which then get uploaded to GitHub or some such thing. And we laugh about those things, but unfortunately they're still happening. Okay, so think carefully about where your secrets are, and make sure that they're either encrypted and protected properly, or stored in some kind of system that is specifically designed to store them and only give them to authorized parties, that kind of stuff. So, for example, in the smart city system, if the bus telemetry ingest is only supposed to accept connections from the Internet of Things gateway, right, to receive the telemetry information from the buses, then that should be an authenticated interface. So that, in a variety of ways, and there are lots of mechanisms you can use to do that, to ensure that only the authorized connections succeed. Don't assume that the attacker just doesn't know where the telemetry goes, because they'll find out, and then they'll be able to inject false telemetry into your system. Okay, principle 5, integrity. This is a fundamental property. Without integrity, kind of everything else falls apart because you can't rely on it. You might say during a security review, well, I know that this access control check will be enforced because here it is in my code. There's no way around it. The check always happens. Great. If your code does not have integrity, if an attacker can reach in and change, your node.js code or your Java jars that you've uploaded, then they can easily make that bypass happen, and then the check that you're relying on is not enforced. So code integrity is extremely important. Protect your code, your source code, and your build system as much or more than your actual production system. Because if the build system gets hosed, you can't rely on the production system anymore. Protect the backups of your code. This next one, be aware of components of your system loaded from elsewhere. And I, sort of ranted briefly earlier about modern platforms and how they load in dependencies. This is a more serious problem than I realized. I was taking a briefing from a specialist security company a couple of years ago, and they gave an example of the provenance and all the dependencies that went into a common open source system. And ironically, it was one that NSA had open sourced, so I kind of felt a little bad about that. Simple system, wasn't that complicated, had over 700 dependencies, out to 5 layers deep, where the main system required X, which required Y, which required Z, which ran out of letters, which required W. That's it's a lot to be aware of, but it's important, because if one of those things had a vulnerability and you didn't know about it, you could be exposed, right? All right. So there are various software analysis tools that can help with that, and if your project depends heavily on external frameworks, then you might consider using that type of tool along with your static analysis and other code checking tools. Okay. Configuration files, obviously extremely important. Treat them just like code. Okay, principle 6. I gotta hurry up because I'm running out of time. Focus on secrets for a moment. Cybersecurity functions and the secrets that go with them are always going to be targets. What's the first thing attackers go after these days when they get to a new system and gain entry? They go after credentials, okay? Whether those are SSH keys or user passwords or Windows authentication tokens, etc. And so think about where those things are. Within NSA, we do a lot of access controls using an ABAC model, and there's a central system that knows all the users' rights and clearances and things like that. That system is protected like crazy because, what users are authorized to what data is sort of central to our entire protection model. And it's also monitored like crazy and so forth. Modern complex systems embed a lot of features that use a lot of secrets, right? Passwords, private keys, tokens, etc. We already talked about the next bit. Segment your secrets. Don't, let's say you get a private key and it's associated with a certificate for your public website. That's great. It's for your public website. Just use it for that. Don't use it for all your internal interfaces, because now you've stored that really, really important private key in 19 different places inside your system. Okay, we talked about crown jewel data already. Oh yeah, some secrets are definitely going to get compromised, right? End user passwords. Some end user is always going to get their password stolen or something. Think about what the impact to your system is, and then build in recovery measures, right? Think about it. If a user called you up and said, so in our smart city example, let's say it was the mayor, just to make a jokey example, says my password to managing the entire subway system has been stolen. How quickly could you turn off all the mayor's privileges so that the attacker that stole his password would have no ability to harm your transit system? Okay. Yeah, that's too complicated an example. We'll skip that one. Okay. Assume your system will have malicious insiders. Unfortunate truth these days. NSA has had its share of issues with this. You can't eliminate that threat because even an insider who isn't malicious but does something accidental and stupid can cause harm to your system. So you have to think about reducing that impact. right? My personal insider threat mitigation model is deter, detect, and defeat. One of the security principles inside NSA is that no action is anonymous. Every action is tracked back to either an authorized user or an authorized system. Not just users have credentials, all the systems have credentials too. And you only want to give each of those entities as much privilege as they actually need to do whatever job they're being asked to do. And then, of course, once you have all this information about who's doing what, you can't just let it sit in a database somewhere. You have to analyze it and look for misbehavior. Okay. So consider an insider in the transit system. They're responsible maybe for vehicle management and maintenance. Okay, this is, an individual who fixes the trains when they break. That's a very, very important job, but it has nothing to do with the ticket system or selling fares or dealing with credit cards. So make sure that that user only has access to the vehicle maintenance logs and things of that nature that they need to do their job, and doesn't have like sort of global privileges throughout the system. And then a really simple analytic that you can use to look for this sort of misbehavior is just looking for permission denied log entries. Average user have a few of those a day. Some person has several thousand. Maybe that's something you'd want to look into. Okay. Understand the security that your system relies upon from external service providers or platforms. This is especially important in sort of hosting provider, cloud provider sort of cases. You're going to write your system. It's going to run off-prem on some cloud service. That's cool. What does it depend on the cloud provider to give you, and what parts do you have to build in? All right, understanding that division it can be very difficult. And then the parts that the cloud provider does offer you, how do you configure those correctly and sustain them over time? Okay, and that applies to sort of your standard cloud providers, Google, Microsoft, Amazon, et cetera. It applies to places where you put your source code and other artifacts like a GitHub, all those sorts of services. Okay. So in the example, right, the vehicle telemetry data is very high volume, so the city is not attempting to process it all themselves. They run it through a cloud provider, and it gets stored there until it can be forwarded. So understand what the cloud provider provides and which bits you have to provide. Okay, we're almost done. Hang in there. And then the flip side of that coin is understand what security your system is offering that others are depending upon. And I've seen this bite folks in my work plenty of times. There was this one particular system that performed a validation check on a certain type of important data. And it was very convenient, it was easy to use, so a whole bunch of other things depended on it. They would like send these pieces of data to the system, it would validate them, report back that one's good, that one's not so good. The folks who ran that system didn't fully understand how many other systems were relying on them and the extent at which they relied upon them. This was accidental, but it could have been a malicious attack. Turned out to be an accident, thank goodness. And that system went down, and like all these other systems ground to a halt because they were all synchronously waiting for their little validation requests to come back, right? And that was an availability attack against one little system, accidental, but it was still an availability compromise where the folks involved had no idea the extent that their little availability interruption would screw up the mission of all these other systems. Okay, your system may be a source of data upon which others rely for its integrity or its confidentiality. They may store data at your system, which they're counting on you to protect, like that other example I talked about with the real-time alerting system. They may count on your system to be able to provide provenance information about data on which they rely, financial data, for example. Okay, in the smart city example, If you remember the diagram, the telemetry data came through our system before going out to the transit engineering systems. And I'm looking back at that later like, was that a good idea? Maybe the telemetry data should have gone straight to the transit engineers, but sorry, we're stuck with it. No budget to change it. So now we have a dependency. The transit engineering system depends on our system to ingest that data with integrity and provide it within certain latency bounds out to the transit engineering system. And understanding that dependency would change how we engineered our system and how we protected it. Finally, number 10, plan for failure. Okay, plan for compromise. Some part of your system will experience a security problem, or it may get compromised through an attack or even an accident, like that example I gave earlier. If you plan for that event, if you think about the failure scenarios that would have high impact for your system, then you can greatly reduce the mission impact. And we all know about simple stuff like assume you're going to lose data and go rehearse restoring from backup. Seen plenty of systems that didn't do that, but still we all know that one already. But somebody red teams your system or does some pen testing against it. Can you see the evidence in the logs? Can you understand what they did? Do you have mechanisms for halting malicious behavior if and when you detect it? Do you have mechanisms, let's say an attacker gets into your system and, three-star general is breathing down your neck saying, I need to know if that data still has integrity, if I can still trust that data, right? And sir, someone may, I don't care if it leaked, I need to know if I can trust it, right? You need to be able to answer that question. Because if you can't, the general is going to assume that he can't trust that data, and mission gets called off, and everything has to be rebuilt, and a lot of problems. So, think about backup and encryption best practices, hold exercises, do rehearsals, drills, that kind of thing, right? And last topic, which I'm going to have to rush through because I'm just about out of time, is maintaining security, right? Complex composite systems are never static. They're always getting new functionality bolted on the sides. Assume your system's going to change. Identify the key elements that can't change because external parties depend on them. That's very important. And then incorporate testing of that sort of into each stage of testing in your pipeline, right? If you're doing some integration tests before something goes out to production, actually attempt some unauthorized things and make sure that they in fact generate the proper permission denied log messages and don't give you data and things of that nature. Okay? This is standard stuff, right? Keep your parts of your system loosely coupled and independent. That's pretty normal. And updates and patches are critical. Make sure that you have the ability to do that and that it's built into your build system. And last one, decommissioning. Someday your system is going to be replaced or taken offline or transitioned to something new, and think about, what am I going to do with all that data? Right? It may be compliance critical or have regulatory implications. I've seen situations where systems at the end of their life were considered no longer important and weren't patched and updated, and then they got attacked. So think about how you dispose of your data, how you transition the critical secrets securely to the new system, preserve the critical logs, and properly dispose of everything else. Okay, so that's it. These are kind of standard conclusions, and I have like 1 minute for any questions. And I'm sorry, I kind of got caught up in my anecdotes, didn't leave enough time for Q&A. But does anybody have any questions about these security principles? That was just 10 out of, however many hundred, but I hope that you felt they were good ones. Okay? All right, I'm out of time. So thank you very much, and please apply these security engineering principles.